Welcome to the Explainer. Today, we are opening up the ultimate survival and colonization manual for the lunar frontier. Imagine trying to build a house, but you have to fly every single brick across a 238,000-mile vacuum. Impossible, right? Well, if you want to know how humanity actually transitions from just planting flags to paving streets and breathing easy on the moon, you are absolutely in the right place. We're going to look at the literal alchemy of Moondust, exploring the fascinating chemical and physical processes of in situ resource utilization, or as it's commonly known, ISRU.
Okay, let's dive into this, because this is really the fundamental logistical paradox of space travel. Earth's gravity well is, frankly, just too deep, and rocket fuel is way too expensive to import an entire civilization piece by piece. I mean, we can't exactly pack up massive concrete blocks, heavy steel girders, and giant life support systems into the payload bay of a rocket and expect to build a thriving city. We have to learn to live off the land. But how exactly do we do that when the land itself is a completely airless dead rock?
So, here is our roadmap for today's explainer. First, we'll cover the industrial MUS/CLE strategy. Second, the chemistry of squeezing air right out of rock. Third, we'll look at the physics of using basalt to fight off deadly moon dust. Fourth, modular biospheres and biomass. And finally, escaping the outpost trap.
All right, Section 1, the industrial MUS/CLE strategy.
This is a brilliant mnemonic from our sources, and it defines exactly how off-world settlements need to operate if they're going to survive. The strategy is to manufacture the MUS parts locally on the moon. Those are the items that are massive, unitary, and simple. Think concrete, heavy metal casings, basic pipes, stuff that's heavy and relatively easy to make. Meanwhile, we continue to import the CLE components from Earth, the complex, lightweight, and electronic items, things like computer chips and highly delicate sensors. So we forge the heavy, basic infrastructure locally, and we only import the intricate brains of the operation.
And this brilliantly illustrates the macroscopic view of this industrial alchemy at work. Just look at the stark contrast here. You've got the raw, pulverized lunar landscape on one hand and highly utilitarian, automated manufacturing on the other. This facility is basically scooping up raw lunar soil, which is called regolith, and processing it right into essential building materials. This is the MUS strategy in full swing. It slashes massive launch costs by making all the heavy lifting happen right there on the lunar surface.
Moving right along to Section 2, chemistry. Literally squeezing air from rock. So the real secret here lies in a local lunar mineral called ilmenite, which is an iron titanate. To get oxygen from it, our sources point to a method called the carbothermal reduction process, and it is a fascinating bit of chemistry. First, you mine the ilmenite and smelt it with carbon at incredibly high heat. This actually separates out the iron, which is then decarburized to make steel. Meanwhile, the off-gases from that smelting process are reformed to create water. Finally, you electrolyze that water, splitting it right into hydrogen and pure breathable oxygen. It's not just basic life support, you are literally co-producing oxygen, steel, and construction slag all at the exact same time.
Now you might be wondering, why use carbon at all? Why not just use hydrogen reduction, which is another pretty popular theory? Well, our sources provide a really clear comparison here. Hydrogen reduction requires you to heat the ilmenite and react it with hydrogen gas, but the thermodynamic equilibrium limits the conversion per pass to only about 5%. It's just incredibly inefficient. Carbothermal reduction, on the other hand, reacts completely in a single pass. A single mass unit of carbon extracts significantly more oxygen from ilmenite than hydrogen ever could, making it a highly, highly effective strategy.
Now, what's really interesting about this slide is the duty cycle breakdown. Whether you're running your processing plant 24/7 at a full 100% duty cycle, or having to power it down during the long, dark lunar night, the carbothermal process proves highly competitive for the mass required to build the plant. And remember that byproduct of iron? That is absolutely crucial. That lunar steel can be used for roadbeds, landing pads, and heavy pressure vessels. It perfectly fulfills our need for massive, unitary, simple components.
Section 3, physics. Using basalt against deadly dust.
Okay, we have to talk about the moon dust problem, because lunar regolith is not like the soft sand on an Earth beach. There is absolutely no wind or water on the moon to weather it down over the billions of years it's been sitting there, so these particles are extremely sharp, jagged, and angular. Imagine trying to build a city in a giant sandbox made entirely of shattered glass and gunpowder.
Worse, they have electrostatic clinging properties from being constantly bombarded by solar radiation. If you try to run traditional metal machinery to mine the stuff, that unweathered abrasive dust will tear through your metal joints and seals in no time flat. It is a lethal threat to our equipment.
So, what's the solution?
Well, physics lets us fight the dust using the dust itself. The lunar maria are super rich in basalt. If we take that pulverized basalt, melt it down in a solar furnace at 1250 degrees Celsius, cast it into molds, and carefully anneal it, it crystallizes. And the resulting cast basalt is unbelievably tough. It actually hits 720 on the Vickers hardness scale. And for context, mild steel is only about 110. It has extreme abrasion resistance, making it the absolute perfect and realistically maybe the only material tough enough to create the pipes, chutes, and conveyor belts needed to handle the deadly lunar regolith.
Take a look at this cross-section of a cast basalt floor tile grid. Because modular lunar structures need curved bottoms to handle the immense pressure differences, you need a flat subfloor over that cavity so people can actually walk around. A simple grid made of alloys or glass can hold these thick, heavy, cast basalt tiles perfectly. It's just the ultimate MUS component. Heavy, low performance, incredibly simple to make locally, and practically indestructible.
And hey, beyond heavy industry, cast basalt can actually be beautiful. By using the tailings and leftover slag from our oxygen and metal processing plants, we can cast tiles of varying natural colors without even needing any sort of glazes. We're talking decorative interior tile trims, baseboards, and coves. It's a great reminder that we aren't just trying to survive in a stark, boring metal can. We are using physics and local materials to create personalized, highly durable, and genuinely livable outposts.
Alongside cast basalt, there is another amazing physics-based miracle material we need to talk about: Glax. Glax stands for Glass-Glass Composites. Because the moon has superabundant silicon, we can melt regolith to create glass fibers and then bind them within a glass matrix. The result? A composite that can be as strong as steel but takes considerably less energy to manufacture than complex metal alloys. Once again, it fits the MUS strategy perfectly, creating massive, ultra-strong structures locally without needing a huge labor force or ridiculous energy grids.
Section 4, Biology. Modular biospheres and biomass.
Now, this is a major conceptual leap. So the crucial point is that this muscle strategy actually applies to biology too. Think about the massive amounts of food, water filtration, and air purification a human crew needs. Shipping that biomass from Earth is just way too heavy and expensive. Instead, bulky biomass, like algae and phototrophic bacteria, must be treated as infrastructure, grown locally. By using anaerobic fermenters fueled by local sunlight, recycled water, and lunar trace minerals, we are essentially manufacturing our biological MUS components right there on the moon.
And we don't just lock this biology away in some sterile lab, we integrate it directly into the architecture itself. A mid-door public space, which is a pressurized common area, beautifully blends indoor safety with outdoor aesthetics. By incorporating modular ecocells and living walls right into the architecture, the outpost's vegetation purifies gray water and scrubs the air locally. Distributing these biological systems is incredibly smart because it prevents a catastrophic single-point failure of a centralized life support system. As the physical complex grows, the biosphere just grows right along with it.
I absolutely love this quote from the source material. In any biosphere, vegetation should play the host to humans, not the other way around. If we want true, permanent settlement, we can't just be tourists living in a sterile tin can, desperately trying to keep a few sad, potted plants alive. We must build integrated, modular ecosystems where the greenery structurally supports us, both psychologically and biochemically.
Finally, Section 5, Escaping the Outpost Trap. Let's move to and see how this builds into securing a real future for off-world humanity. You see, the outpost trap is the constant looming danger of relying entirely on Earth for survival. It turns a settlement into just a temporary science base that inevitably gets abandoned the second budgets dry up back home. True autonomy is only achieved by mastering the chemistry of ilmenite, the physics of cast basalt and glassix, and the biology of modular ecocells. By completely mastering the industrial MUS CLE strategy, we replace those heavy earth imports and finally create an independent, truly self-sustaining world.
Which leaves us with this final, massive question. Will our next lunar mission be just another temporary outpost, basically a quick camping trip in the void? Or will we use the alchemy of Moondust to pour the permanent foundation of an independent world? The blueprint is literally right there in the chemistry and the physics. It's up to us to build it.
Thank you so much for joining me for this explainer. Keep learning, and I'll see you next time.